This is the answer key for bonds and dipoles. When we're doing bonds and dipoles, we need to come up with two different definitions of bond type. We have both atom type definition and electronegativity definition. Please recall on bond type definition, or atom type definition, on the periodic table, you can basically split it into metals and non-metals. So you'll need a periodic table to complete this worksheet. And remember also that hydrogen is actually a non-metal, even though it's hanging out with the rest of the metals on the periodic table. So to solve the first column of this sheet, look at the atom, decide where it lives. So nitrogen lives in the non-metal side, NM. Fluorine is also a non-metal. Non-metal to non-metal. Equals covalent, which means metal to non-metal equals ionic. So for the first problem, a non-metal to non-metal is covalent. Hydrogen to fluorine. Hydrogen lives on the left, but remember that is the one, the one that kind of plays a trick on you. So that's also a non-metal to non-metal, which makes this covalent. Magnesium's a metal, chlorine's a non-metal, makes this ionic. Oxygen stuck to itself is non-metal, stuck to non-metal, covalent. Potassium's a metal, nitrogen's a non-metal, which makes this ionic. Lithium is a metal, sulfur is a non-metal, which makes this ionic. Carbon is a non-metal, oxygen is a non-metal, which makes this covalent. Aluminum is a metal, bromine is a non-metal, which makes this ionic. Aluminum is an atom that students commonly think is a non-metal, and that's because they see that aluminum is underneath the word non-metals. Students think that this whole rectangle is non-metals. However, non-metals are to the right-hand side of the stair-step line. And finally, hydrogen, we already said, was a non-metal, and oxygen is also a non-metal, which makes this thing covalent. I'm able to fill in metal and non-metals because I know where these atoms live. You might need to find each atom symbol, like magnesium, find it on the periodic table, decide if it lives on the left of the periodic table stair-step line or the right-hand side. That's how I figure those out. I just know where they are. So that was the type of bond based on atom type. We're also going to figure out the type of bond based on electronegativity. So we're looking at the difference in electronegativity. So that means subtract. We're going to do big minus small. And if the value is less than 0.3, we're going to call that non-polar covalent, which means completely even sharing of electrons. If the number is 0.3 through 1.7, electronegativity difference, we're going to call that polar covalent, which means uneven sharing of electrons. And finally, if the difference in electronegativities is greater than 1.7, we're going to call that ionic. To figure out electronegativity values, you need to have a resource that provides those. We happen to have a Pogo packet that provided some of these electronegativities. Notice that many of these electronegativities have values out to the 100th place value. For simplicity's sake, we're just going to round those to the tenths. So when I'm saying the numbers, I'm going to round these values to the 10th place value. So nitrogen's value is 3.04, which rounds to 3.0. Fluorine is 3.98, which rounds to 4.0. 4 minus 3 gives me 1.0. 1.0 value, if I look back up on my values in the top, puts me into polar covalent. Hydrogen is 2.2. Again, that's from my resource. We already used fluorine right here, 4.0. 4 minus 2.2 is 1.8. That puts me above 1.7, so that's ionic. Magnesium is 1.3. Chlorine is 3.2. 1.3, 3.2 minus 1.3 is 1.9 difference, which gives me ionic. Oxygen, so two oxygens stuck to itself, so it's going to be the same number for both. So really the same number is going to be 0, which makes this nonpolar covalent. Complete even sharing of those electrons. If we were to actually look up the values, they'd both be 3.4. Potassium is 0.8, and nitrogen is 3.0, giving me a 2.2 difference, which makes that very ionic. Complete transfer of those electrons. Lithium is 0.98, which makes that 1.0. Sulfur is 2.6, making a difference of 1.6, which just makes that range, making this polar covalent. That's pretty close to ionic. Uneven sharing of electrons. Carbon is 2.6. Oxygen we use up here, 3.4, making a 0.8 difference, which is polar covalent. Aluminum, the table says, is 1.6, and bromine is 3.0 for a difference of 1.4, making this polar covalent. And then lastly, hydrogen we've already used at 2.2, and oxygen we've already used at 3.4 for a 1.2 difference, making this also polar covalent. So notice that some of the bonds that we classified as ionic using the atom type definition actually turn into polar covalent. This column is a better description of actual properties of bonds and materials that are being held together by those bonds, whereas this definition is very useful to us when it comes to formula naming and compound writing. The last column is dipole moment. If the bond is polar covalent, prefix di means two, and poles kind of mean ends. So each of these bonds has two ends, a positive end and a negative end, or partially positive, partially negative. The large electronegativity value is assigned to the atom that really likes electrons. And since electrons are negative, whichever of these two atoms has the larger value is going to be partially negative. To draw a dipole moment, we're going to take the two atoms that are in the bond. So in this first problem, it's nitrogen and fluorine. We're going to connect them with a single bond, like so. We're going to look at our two electronegativity values. The one that's larger is going to have a negative sign written above, and the one that's smaller is going to have a positive sign. Now, if you go bow hunting for deer in the fall, you shoot arrows, and arrows have the feathered end and the broadhead end. So I can kind of draw my arrow for my dipole moment using the plus sign as the feathers and the minus sign as the broadhead. Now this arrow shows where the electrons are. So really, covalent bonds are sharing of electrons, but since this is polar covalent, this arrow is basically showing that the electrons are headed more towards fluorine than they are for nitrogen. They're not right in the middle. This is the dipole moment, but it's really indicating that electrons are flowing towards fluorine, making fluorine partially negative. You don't need to do this one, or this one, or this one. For oxygen, though, since it's nonpolar covalent, what that's indicating is that those two electrons in that bond are directly in between the two oxygen atoms, which makes that very equal sharing. Don't need to do ionics. Lithium with sulfur. Sulfur's value is 2.6, which makes that negative, makes lithium positive. Draw your arrow. pointing to a negative, larger electronegativity. Carbon-oxygen bond, likewise, oxygen's value is larger. An aluminum-bromine bond, bromine's value is larger, pointing electrons towards bromine. And finally, a hydrogen-oxygen bond. Hydrogen's value is smaller, oxygen's larger, pointing electrons towards oxygen. You can also draw this the other way, and if you follow the directions of whichever atom has a larger electronegativity value, 3.4, that's negative, positive, point your electrons towards the larger En value. And that's the answer key for bonds and dipoles.